the average value of this function f is a number, and more specifically is a fraction, and still more specifically is a fraction when the numerator is simply the definite integral of this function f from a to b of this function f of x dx, and this this number is divided by the length of the domain of this function, which is simply b minus a. So the whole thing is divided by b minus a. And this is the average value of the function. By definition, the intuition is that if this is the function f, then at this point, somewhere here, the function will have maximum. The function will have maximum. And then somewhere here, the function is going to have, somewhere here, the function will have minimum. The function will have minimum. And, okay, so here's the maximum, here's the minimum, and there's a lot of values in between. You know, there's a lot of values in between, and somewhere in the middle is the average value. And on this picture, that would be somewhere here. This is the average value, f a v e, average value of this function. Well, there's a simple definition, but the point of this is, and this is the main result of this section, is the mean value theorem. The mean value theorem, this is the main result of this section. And what does this says is the following. Well, let's say you want to compute the definite integral of this function from a to b of this function f. Okay, what does this mean geometrically? It simply means that this is the area underneath the function. This is the area underneath the function. So let me just, this area underneath the function. This is the definite integral of this function f is simply the area underneath the function. But this area is difficult to compute because the shape is not a regular shape like something that we know how to compute the area of. But if you know what is the average value of this function, then this is actually equal to the area of an appropriate rectangle. Rectangle, the base of which is simply the length of the domain of this function b minus a. B minus a. But the point is how do you find the height of this rectangle? The appropriate height, that would be exactly the same as the area underneath the function, or in other words, as the definite integral. And the height of this rectangle is exactly the average value of this function f. So this number, f a v e, the average value is the height of this rectangle. So on one hand side, you have definite integral, and this is maybe difficult to compute. But look at this function f. If you can find the average value of this function f, then you can find a rectangle, the area of which will be exactly the same as the area of this definite integral. Well, the base of this rectangle is simply b minus a, but the point is, how do you find the height of this rectangle? And the height of this rectangle is precisely the average value of this function. So we did a couple of examples last time. So this is just a reminder. So we won't be doing details, but that's the whole point of this section. So see, the rectangle is actually this one. This is the height of this rectangle, which is exactly the same as the average value of this function. And this is the rectangle. The area of this rectangle is exactly the same as the area underneath the function, in other words, as the definite integral. So that was the whole point of this section. So two things in this section. One is the definition, and this is the definition of the average value of the function. Average value, so the function has minimum, the function has maximum, and so many values in between, but somewhere in the middle is the average value of this function. And that's exactly this number. It's given by this formula. And then the mean value theorem says that if the function is continuous, then you can find a point C in the domain of this function so that f of C is exactly equal to the average value of this function. Average value of this function. Okay, so that was a very quick reminder. That was a very quick reminder what we did last time. That was section 6.2. So today we would like to do a new section, and that's the section about volume. You know, that's the section about volume. So today, today we'll be doing section 6.4. So here's the plan for today. The plan for today is to do section 6.4, and this section is about volume. So 1 second introduction. What is volume in first place? It's a measure to measure a three-dimensional object or shapes, for example, an apple. Well, let's start from one dimension. We'll get to dimension 3, but in 1 second, let's start from dimension 1. Okay, so let's start from dimension 1. And dimension one is simply a straight line. So here's a straight line. Here's a straight line. And we can measure straight line using simple ruler. So for example, from here to here is maybe 1 centimeter. So from here to here, maybe this is, okay, this is the X, or maybe this is the Y axis. So this is 0, this is 1, maybe there's 2, and so on and so forth. So if I take this interval, so for example, from 0 to 2, then I can measure the length, and the length of this interval is 2. It's simply b minus a, so 2 minus 0 is 2. This is the length. And length is a measure of a straight line, or it could be a little bit more general, but now, so this is dimension, so this is dimension 1. Let's do to one more dimension 2. So this is dimension 2 now. And in dimension 2, if we have something on the plane, for example, a rectangle, then I'm not using length to measure the air, to measure this surface, but I'm using area. And area is simply the base. So for example, maybe this is 2. I can measure the length because this is a straight line. And then I can measure the length of this side because length is something one-dimensional. So I'm using this to measure one side, to measure the other side. And simply this is the area would be 2 times 3. So this is the area. And we use area for two-dimensional objects. But in dimension 3, this is a point of interest for us. This is dimension 3, because in dimension 3, this is very something useful because we live in this dimension. Everything is three-dimensional, so we want to measure volume of a three-dimensional solid. So for example, if I have this cube, it's not really a cube, but cuboid or something like this, then I know how to compute the volume of this thing. So it would be this times the height. So this is dimension 3. Okay, so this section 6.4, this section is about how to compute volume of three-dimensional things. And when we have this kind of cube, or maybe cuboid or something like that, then we know how to compute volume. But the point is, if you take something three-dimensional like this grape, for example, or maybe this apple, So today what we'll be doing today is we'll be computing the volume of this apple actually. This is something as an example of how to compute volume of a three-dimensional solid. So first of all, let me give you the very basic things. For example, this is a three-dimensional solid. Is a three-dimensional solid. It's a cube. Right? This is just an example of a cube. And let's say how to compute. Well, we know that this is just a reminder. If the length of one side is equal to A, so the length of this side is also equal to A, and the length of this side is also equal to A, then the volume V of this cube is A times A times A, so A cubed. Okay, so one cube that we are very familiar with is this one. So that's a Rubik's cube. And let's say what's the volume, what is the volume of this Rubik's cube? So let's say that for me, this is 1 unit and I use this for length. So this is the length of this one is 1, and the length of this one is also 1, and the length of this one is also 1. So the length of this side is 3, and so is the length of this side also is equal to 3, and so is the length of the height, so it's also 3. So what is the volume of this cube? Well, this is going to be 3 times 3, and then times the height, times 3. So this is 3 cubed. And that's the volume of this cube. And then if we choose that for me, this is 1 unit. This is one unit U, whatever the unit might be, a centimeter or kilometer or anything that we want to, but we have to specify a unit. Once I specify a unit, then this will be 27 units, those units but cubed, because we are in dimension 3. Well, that's something very simple to compute. This is just a little bit more general, so take something, not a cube, but they call it usually a cuboid. So it looks like a cube, but the length of this one and this one and this one is not necessarily the same. So let's say that the length of this is W, and the length of this side is L, and the length of the, see, I'm using length to compute the length of this straight line because this is one-dimensional. And then I combine those in the following way to get the volume. So the volume of this would be simply L times W, and then times the height. And again, some units cubed. I choose some units, so maybe for me from here to here, this is 1 unit. For example, 1 meter. Or 1 unit U, call this U for example. Then the volume of this would be L times W times H into number, and then units cubed. And this is a rectangle, so, excuse me, this is a cone. So base of this cone is a circle, and this has some height H, and the side length is L, and this is the radius of the base. That's how we can compute the volume of a right cone. And this is a cylinder. So the base of the cylinder is also a circle. It has a height, so all I have to do is I have to know the radius. And notice one thing. So pi times the radius squared, pi times the radius squared, pi times the radius squared. This is exactly the area of, okay, let me ask you this question. What is this formula for, so this is the area of what shape? Pi times the radius squared. Perfect, this is exactly right. This is the area of the circle of the base. So what we do is I have to find the notice one thing, area. So this is the area of the base. This is the area of the base. And then what I do is I multiply this by the height. Multiply this by the height. Well, we'll get back to this in a second. There'll be something. Okay, so this is the volume of a cylinder. This is the volume of a sphere. And today we'll be computing this. So this is the formula that we know, but we will derive this formula and we'll be computing volume of an apple. So, and there's basically, this is some kind of classification of the simple three-dimensional solid. And the main question is now, okay, how do you actually compute the volume? What's the most significant thing to know? And what will be the process of computing volume, all of this? So the key point in this section is the idea of cross-section. The main idea, let me just see. Okay. Yes, those are the yes. Platonic solids, exactly. Perfect. Excellent. Okay, so the key idea in this whole section is the idea of cross-section. So what I want to do is I want to say a few words about what is cross-section and then how to compute volume of a three-dimensional solid. So cross-section is when you have a three-dimensional solid, for example, the cylinder, and then you take the intersection of the cylinder with a plane. So you take a plane, so for example, here's some kind of plane. You take a plane, you take a plane and you do the intersection of those two things. So we'll take an apple, for example. We'll take an apple and a plane. And then when I do the intersection of those two objects, on one hand side, the apple, and on the other hand, the plane, that will give me the cross-section, the corresponding cross-section. This is, on one hand side, that's super simple, but I want to say a few words about this because this is going to be super important, the idea of cross-section. On the other hand, take this kind of pyramid, and cross-section is, again, what you do, you take a plane, just a piece of paper. And so take a piece of paper and you do this kind of, I don't really know how to draw this, but you do this kind of intersection. And the intersection of those two objects, on one hand side, the plane, and on the other hand, the pyramid, that will give you the cross-section. So the cross-section is basically intersection of the plane with a three-dimensional solid, for example, an apple. So let's do some practice. Let's take this pyramid again. And because we need to do some calculations, so let's place this, or let's introduce some coordinate system. So the y-axis maybe is going to be, this is going to be my y-axis, let's say. Okay, and this is going to be my x-axis. Sorry. So this is my x-axis. This is my y-axis. Let's do some practice with the cross-section, how to get the cross-section. Okay, so let's take a plane. Maybe let's do this on, so this is 0, this is 1, this 2, this 3, this 4, this 5, and there is 6. Okay, so the height of this pyramid is 6. Let's do a couple of cross-sections. So to specify a cross-section, you have to specify the level. Let's say, quote unquote, the level. What do we mean by this? So let's do the cross-section on level 4, for example. So on level 4, I'm going to take a piece of paper and I'm going to cut this pyramid on the level 6. So my piece of paper will be something like this, something like this, something like this. Okay, and this is the intersection of the plane and the intersection of the pyramids. So here is how my cross-section looks like. So cross-section is just a rectangle. This is the corresponding cross-section. So this is the cross-section that corresponds to y equals 4. This is very important. That's a cross-section that corresponds to y equals 4. In other words, the cross-section is on level 4. I can do another cross-section. I can take a piece of paper like this one, for example. Like this one, for example. And this is also a cross-section, but notice that the cross-section will be a little bit bigger. On level 2, the cross-section is going to be a little bit bigger. So this is the cross-section that corresponds to y equals 2. In other words, this is the cross-section on level 2. This is the cross-section that corresponds to y equals 4. And let's do maybe the base one. The base one would be actually when you do the cross-section on level 0. You know? So here, well, let me admit those two people as well. Okay. Don't be like people, please. So what I was saying is this. Let's do the cross-section on level 0. And notice one thing. The cross-section is also a rectangle. This is on level 0, or this is the cross-section that corresponds to y equals 0. And now notice very important thing. The cross-section is a rectangle on this level. The cross-section is a rectangle on this level, and so is on this level. But the point is that the area of this rectangle is smaller than the area of this rectangle, and this rectangle has area even bigger. So the area of the corresponding rectangle is a function of y. This is the corresponds to y equals 0. This is the area, this is the cross section that corresponds to y equals 2, a of 2. So the area is a function of this height. If you stay very close to the top of this solid, then the area of the corresponding cross section is small. On the other hand, when you stay close to the base of this solid, then the area of the corresponding cross section is big. So the area A is a function of y, And this is going to be something that we'll need to compute volume. But for now, we're practicing what is cross-section, and we have noticed, and we already noticed that to compute the area of the cross-section, the area of the cross-section will be a function because it will depend on the level, the position of the cross-section, you know? So let's compute the volume of something simple, just to get some practice, and let's compute the volume of this, of the cylinder. So I'm going to introduce a coordinate system because we'll do some calculus, so we need a coordinate system. Anyway, so this is going to be my y-axis, let's say. And I place the y-axis exactly in the middle of this cone, or of this cylinder. Okay, so I'll place the y-axis exactly in the middle. And I will place the x-axis like this. Okay, now we have something to make reference to my coordinate system. And so this is my x-axis, this is my y-axis, and let's say that this is 1 and this is 2. So it means that the base of the cylinder is a circle of radius 2. And let's say, for example, the height is 8. Just for example, maybe this is 1, 2, 3, 4, 5, 6, 7, 8. So the height of this cone or of this cylinder is 8. And the radius of the base, is 2. Okay, so how do we compute volume? First of all, we'll be doing cross-section perpendicular to the y-axis. Or you might say orthogonal to the y-axis, the same thing. So what it means is I'll take a plane and I will be doing the cuts like this, as opposed to like that. We can do so as well, but simply this will be just the reason I'm doing so. It will be more convenient. The computation will be easier. I could do cross section also that way, but in this example, I'll be doing this that way. So my cross sections will be orthogonal to the y-axis. Okay, so let's pick any point y that is between 0 and 8. Let's say, for example, this is my point y. It's any point between 0 and 8. And now I will be looking at the cross-section that corresponds to this given point y. So what I do, I'll take a piece of paper. And on level, the y could be any number, for example, 1, 2, 3, 4, or 7, anything between 0 and 8. And now I'm looking at the cross-section that corresponds to this given point y. Well, here's the cross-section. Here's the cross-section that corresponds to this point y. Okay, what is the shape of the cross-section? Very simple, a circle. The shape of this cross section. This is exactly the cross section. This is exactly the cross section that corresponds to this point y, is a circle. Okay, so I want to now compute the area A. I want to compute the area A of the cross section that corresponds to this given point y. Okay, so here's a question for you. First of all, what is the radius of this cross section?
2.
2.
Perfect. This is exactly 2. So the radius of this cross section is 2. But now we know how to compute area of a circle. So area of a circle is simply pi times the radius squared. So in my example, this is simply pi times the radius is 2, and then square it. So this is equal to, this is 4 times pi. And I took this example just because it's very simple, because notice one thing, in this example, the cross section will not change. We'll get a function of y, but it's a constant function, because at any level between 0 and 8, at any level between 0 and 8, the cross section is the same. It doesn't really change. So we have a function, but the function is a constant function. It's a constant function. So a of y, so we have the formula a of y is equal to 4 times pi. It's a constant function, So now to compute the volume of this three-dimensional solid, is what we do is we will integrate cross sections. So essentially we'll integrate from 0, so from 0 all the way up to 8 of this function a of y dy. Okay, so this is integral from 0 to 8, 0 to 8. A of y is a very simple function, it's 4 pi dy. Okay, so this integral is equal to 32 pi. So that's something super simple to compute, 32 pi, and that's the volume of this cylinder. So this is what we'll be doing. It's just one example that this is how we'll be computing volume of a three-dimensional solid. So what we do is we have to come up with this. Let me admit those 2 people as well, but please don't be late, people. Admit it. Okay, don't be late, people, please. So what I was saying. So In this example, the cross-section is very simple because it doesn't really depend on this height. It doesn't really depend on this height, but if this is a different shape, maybe it's maybe a cone, then this will be a function of y. So let me give you another. Okay, so this is the computation that we have just done. So I put this as a PDF file on our class website. So if you would like to, you're most welcome to go over the computation as well. So the idea was to compute the volume of this cone. And what we did, we took some y between 0 and 8. So this is the point. And then we have this is the area of the cross section corresponding to this given point y, corresponding to this given point y. So what you do, you take a piece of paper and you look at the corresponding cross section, and then you compute this area. You compute this area. This is the area A, but it's a function of y. In this example, it's a constant function, but in general, it doesn't have to be a constant function, and we'll see many examples when it's not. And then to compute the volume, you look at the integral, and then you basically integrate all of the cross sections from 0 up to 8, because the height of this was 8, from 0 up to 8. We can do up to 9, for example, then the integral will be from 0 up to 9. Okay, and this is very simple constant function, so very simple function to integrate. So that's this. So let's do now another example when the cross section will not be a constant function. And this was, I want to compute now the volume of an apple. And we'll think of this as a sphere, of course, just for simplification. But again, idea is the same. The idea is look at the cross section. But now let's look here. The cross section is going to be a function. This is a sphere, or think of this is just an apple. And then I will be looking at the corresponding cross section. I can do this either orthogonal to the y-axis. So for example, see, this is my cross section on a different level. So there's no intersection, but then here the cross section is small, and there's this bigger and bigger and bigger and bigger. So this is the intersection of this apple and this plane. And this plane is now orthogonal to this is the y-axis, and is orthogonal or perpendicular to the y-axis. We can do the same, and we can change this, and the plane will be like this, and they'll be orthogonal or perpendicular to the x-axis. We can do this as well. Let me show you how this looks like when the plane is orthogonal now to the x-axis. Same idea. So my plane now looks like this. And my cross section will be also a circle, but notice one thing. The circle, the cross section now is a function of, see for example here, this is the cross section that corresponds to some specific point on the x-axis. And here's the cross section is a circle. But when I do this cross section a little bit more to the right, the circle is smaller. So the point is now that the cross section will be a function of x. So what I want to do is I want to introduce a coordinate system. So I'll place the coordinate system for convenience exactly in the middle. So here, exactly in the middle. So this is going to be my x-axis. This is going to be my x-axis. This is going to be my y-axis. Or no, this is the x-axis. This is the y-axis. Okay, and let's say this is 0. So this is 0. And let's say the radius of this apple is some number r. So from here to here, this is the radius, maybe 7, for example, and then we can choose any number we want to, or 7 divided by pi, for example. So this is the radius. And now I am looking at the corresponding cross section. So the cross section, okay, question for you. Let's fix some point, maybe x. Let's fix some point x in between 0. So here's 0, and here's the radius. In between 0 and the radius. So one thing what I want to do is I want to compute the volume of an apple. One thing what I want to do is I want to cut this apple through, and I can compute the volume of half of it. So let's compute the volume of half of it, because the other half will be symmetric. So let's just do the volume of this semi-sphere. So from 0, just this half, from 0 up to the radius. So I'm fixing any point x between 0 and the radius. This is my point x, and this is the corresponding cross-section. The cross-section is a circle of some radius. So I want to compute the area of the cross-section. I want to compute the area of the cross-section. So let's see. Okay, so the radius of the circle is from here all the way up to here. This is the radius of the circle of interest. Because once I know the radius, then I know how to compute the area, because it's pi times the radius squared. So what is this length in terms of x? Let's try, let's see. So another question for you, what is the distance from here, from 0, up all the way up to this point of the sphere? And this is what I want to know. This is the radius of the cross section. So let me call this y just for a second. Let me call this y just for a second. Okay, so we know that x squared plus y squared. So x squared is this, y squared is this, and that's equal to the radius squared. Okay, so in other words, y squared is equal to the radius squared minus x squared. And so y is equal to the radical of r minus x squared. So this is exactly the y. This is exactly the radius of the corresponding cross section. That's a cross section that corresponds to this given point x. And so now the area A of the cross section that corresponds to this given point x, so the area is a function of x, is pi times the pi times the radius, and then I have to square it. Okay, so pi times the radius. What is the radius of this cross section? Is y, but y is exactly this. We have computed what y is. So this is the radical of r minus x squared. Okay, so a of x is going to be equal to pi times, this is a radical and you square it. So essentially you get the radius minus x squared. Perfect. See, this is the area. So we have this cross section. The cross section is circle, and this is exactly the area of the cross section that corresponds to this given point x. So this is exactly the area of the circle. Okay, so now, and notice that this area is a function of x, because when we'll be moving this x to the left, to the right, this area will be different. Okay, so now the volume, but let's say the volume of the sphere, and I'll take 1/2 of this. 1/2 of the volume, so the half of this volume, so this part, this part is going to be integral from zero all the way up to this point, all the way up to the radius, whatever the radius is, of the function a of x, dx. And you know that was just one example, but this is how we'll be computing the volume of. The key point is step 1, come up with this idea for the cross sections, and 2, integrate cross sections. So when we do the computation, and then we multiply everything by 2, that will give me the volume of this sphere. And I have done this computation over here. So first of all, come up with this function a of x. So a of x is the function pi times this. This is the area of the corresponding cross section. This is the cross section that corresponds to this given point x, and that's the area of the cross section that corresponds to this given point x. And notice one thing, this area is a function of x. And it's reflected in here, because when you'll be moving this point x to the left, to the right, this area will be different as well. In other words, the area is a function of x. And then what you do to compute the volume of this whole thing, of this apple, what you do, you have 2 times. And the reason we have 2 is because this is the half volume. So that's why I'm multiplying this by 2. Well, and then this is a function that's very easy to integrate. That will give you the volume. And notice one thing, when you go back to this slide, well, we have this formula, but this is exactly what we have proved now. This is exactly our computation. This is exactly the volume of the sphere. So take this function y equals square root of x. That's the function. The function looks like this. Now take another function, y equals 1 divided by 10x. So the function is essentially a straight line, but the slope of this straight line is 1 over 10. So here's how this function looks like, something like this. And take this straight line x equals 4. So the line x equals 4 is just this line. So this is 1, 2, 3, 4. This is x equals 4. Now those 2 functions in this line, they enclose a region. They enclose a region. So here I indicated this region in red. And now what I want to do, I have this region, I want to do the revolution about the x-axis. So for now, this is a region, but when I do the revolution about the x-axis, I'll get a 3-dimensional solid. So when I do the rotation about the x-axis, I'll get a 3-dimensional solid that looks like something like this. I don't know what's the name of this shape, but it looks something like this. And now the point is, let's compute very quickly the volume of this thing. So again, here, x is, I can introduce the x-axis like this in here, and the y-axis is in here. So x will be any point between 0 and 4. And what I'm computing in here, a of x, is the area of, this is the corresponding cross-section. That's the cross-section that corresponds to a given point x in between 0 and 4. So this is simply area of the big circle, which is pi times this squared, minus area of this small circle, which is pi times this. And then what I do to compute the volume, I will integrate the cross sections from 0 up to 4. So now I have more general situation. I'll take 2 functions. Here's a function f, and here's function g.
Shown in this picture.
I want to mute this. Okay, I have 2 functions. One is function f, one is function g. I am looking at the region enclosed between those 2 functions f and g. And then what I want to do is I want to do the rotation about the x-axis. When I do so, I will also get a 3-dimensional solid. And the solid one looks like this, something like that. So we can call this solid, I don't know, maybe S or something like this. But it's a 3-dimensional solid. And what I want to do is I want to compute the volume of this solid. And we can do so in the following way. So this is the beginning of the solid, and this is the end of the solid. And for any point x in between this point and that point, I'm looking at the corresponding cross-section. And the cross-section looks like, see, the cross-section looks like one circle with a small circle inside removed. So the area of this is the area of the big circle minus the area of the small circle. And then to get the volume, I will integrate this function a of x from a to b. Okay, so first of all, I want to compute the, for those of you, some people have classes, so I won't be saying anything new. I want to, if you would like to stay, you are most welcome. We'll do this example again, and we can think of this as office hours. So I want to compute the volume of this apple. First thing to do is I'm going to take half of this apple. Okay, first thing to do, and this is related to your question because this is why this is half. I'm going to take half of this. So, and then I'm going to introduce the coordinate system. So my x-axis will be something like this. And my y-axis will be something like this. And let's say we are computing now just the right-hand side half of this apple. So just this half. Just this half. This is very much related to your 2 question, but okay. So this is the x-axis, this is the y-axis. And then, okay, let's say that the radius of the sphere is some r. It's some number, for example, 17 or any number, any positive number, and here is 0. So now I'm focusing just on this half of this apple as opposed to the whole thing. That's because it's symmetric. When I compute the half of this apple, then the other half is going to be exactly the same because it's symmetric. So that's why we'll have the 2. But that's one step at a time. So I need cross sections, and I'm going to fix any point between 0 and the radius, maybe this point, and call this point x. So x is completely any point in between 0 and the radius. So here's my point x, and now I am looking at the corresponding cross section. So here's the cross section. So here's the cross section. So I'll take a plane, and here's my plane. Okay, and here's my plane. And this is the cross section that corresponds to this given point x. The whole point now is to compute this area. Well, the cross section is a circle, and the whole point is to compute this area of the cross section. So let's see. From here to here is x. But now I know that from here to here, what is the length of this one from here to here? What is the length of this line segment?
R.
Perfect. This is exactly the radius of this apple, or this is exactly r. Perfect. And this is what I want. I want to know what is this? What is the length from here up to here? This is what I want because that's the radius of the cross section. So let me call this y. Just for 1 second, just for computation, I would like to know what is the y. So let's see. I know that x squared plus y squared is the radius squared. X squared plus y squared is the radius squared. And I know what the y is equal to, so I can compute it from here. So y is equal to, this is the radius squared minus x squared. Okay, so when I take this is y squared equals this minus that. So excuse me. So when I take the radical of both sides, I'll get that y is equal to the radius squared minus x squared. So this is exactly what y is equal to. This is the radius of this cross section. So what is the area? What is the area of the cross section? The area of this cross section, first of all, is a function of x. Is a function of x, but the area of this specific cross section is going to be equal pi times the radius, and I need to square it. The radius from here to here is y, but I know that y is this number. So I can say that a of x is equal to pi times, when you square this, then you get this is r squared minus x squared. Okay, so what this is the area of the cross section that corresponds to this specific point x. So that was my point x, and I have computed the cross section of this. Okay, so now the volume of one half of the sphere, So in other words, now I can tell you what is the volume of this half. See, of this half. So the volume of this half of this sphere is very simple, because it's the integral from 0 all the way up to this number radius, from 0 all the way up to this number radius, of what function? Of a of x dx, which is this function. A of x dx is pi times r squared minus x squared dx. Okay, so now the volume of the whole sphere, the volume of the entire apple of the whole sphere is equal to 2 times, and the reason why this is 2 is because on one hand side we have computed the volume of half of this apple, and the reason I have 2 because I have another 2, and when I take them together, that will give me the volume of the whole sphere. So 2 times the integral from 0 up to the radius of this function. So pi times the radius squared minus x squared dx. Okay, so your question is, why do we have the constant 2 at the front of this integration? The reason we have the constant 2 is because what we did was initially we said, okay, I want to compute the volume of this apple. First thing to do, notice one thing, that this apple is symmetric, so I can take away 1/2 and I can focus on just 1/2 of this apple. And this is exactly the formula for the 1/2 of this apple is this. But then what we did, okay, so if I know what is the half of this apple, then the other one is symmetric, so I can multiply everything by 2. And that's what the 2 here is responsible for. That's what the 2 here is responsible for. And I have done this computation over here, so that's why we have the 2